Evidence number 4. Uranium and polonium radiohalos. Now this is highly complex, and we're going to have a whole session on it on Thursday night. So if you haven't understood this time around, come back on Thursday night. But it's not that difficult to understand. Again, we go to a granite, say in Southern California, east of San Diego. Most granites contain a flaky black mineral called biotite. It's a mica mineral. You can peel the flakes apart. There's a white mica and there's a black mica. The black one is called biotite. And inside these biotite crystals, we find zircons. Again, this interesting crystal called zirconium silicate. It's interesting because it has uranium atoms in it, okay? But these radioactive uranium atoms are spitting out these alpha particles, which is the name of there's 2 neutrons and 2 protons that the nucleus spits out to reduce its size to become more stable. And we call the 2 protons and the 2 neutrons together an alpha particle. That's alpha decay. Okay, but once that's happened once, the parent uranium atom has become another daughter atom, but that's still unstable. It decays again. In fact, to get down to lead, there are actually 8 steps where these alpha particles are spat out like little bullets from the uranium atom to make it more and more stable till it eventually gets down to lead. And so you have here a radioactive uranium atom. It spits out an alpha particle, becomes a daughter atom, spits out another alpha particle, and does it 8 times altogether before it gets to the lead atom. Now, why is this significant? Well, let's go further. When the zircon crystals are large, as in the first example I gave you from that drill hole in Los Alamos where we got the helium studies, where the zircon crystals are long enough, are big enough, the alpha particles can't escape. They don't have enough energy to escape from the zircon crystals. They pick up stray electrons and become helium atoms, which is why we had helium in those zircon crystals. But when the zircon crystals are tiny, the alpha particles escape and they shoot out like little bullets into the surrounding biotite crystal. And it's like firing a gun at a plasterboard wall. You leave a hole in it. So these alpha particles are so energetic that they damage the surrounding crystal, and it damages it and discolors it. And so you can see here an example of, in the center, you can see a tiny little zircon crystal, and you can see the discoloration around that zircon crystal because of all these little bullets, radioactive bullets coming out. It's like when they used to use radioactive decay. You put a piece of uranium on a photographic plate, it would leave a darkened area. Well, it's similar in a biotite crystal. And these are called radioactive halos, or radiohalos for short. And they are evidence, they're physical evidence of abundant radioactive decay. Now, interestingly, each of these steps, and I said there are 8 steps from uranium down to lead, every one of those steps produces alpha particles or bullets of different energies. What does that mean? It's like having a handgun versus a rifle. The rifle's got to shoot the bullet further than the handgun. And so these alpha particles go different distances, and so the sphere of discoloration is at different distances according to what element in that decay chain shot out those little bullets. And you can see in this diagram the list of parent atoms that shoot out the alpha particles from uranium all the way down to lead, and the different energies. And where the bullets stop, they produce the most damage, which produces a darkened ring. So a fully formed uranium radiohalo has 8 rings, as you can see in that photograph. And it has been determined that to form this discoloration at such an intensity that it can be observed under a microscope requires 500 million to 1 billion of these alpha particles. Now, that much decay is equivalent to at least 100 million years worth of radioactive decay measured at today's rates. So when you see these radiohalos in a granite, it means that that granite has suffered at least 100 million years of radioactive decay. That's at today's rate. I'm not saying the million years ever happened. All I'm saying is if you take the measured rate today and extrapolate it back, that's the number you get. Now, granites all around the world contain these dark uranium radiohalos, and I've had samples now from 4 or 5 continents. And everywhere I look, I find these radiohalos. And so we go to Arizona in the Grand Canyon area. We go to southern Australia. We can go to southeastern Australia. We can look in England, the Lake District of England. We can go to the Confederate Memorial outside of Georgia and find these radiohalos. Don't tell them I got samples from there, will you? And also you can go to Yosemite National Park and find halos in rocks like the Half Dome granite. So, granites all around the world contain this abundant physical evidence of nuclear decay, at least 100 million years worth. And interestingly, you need to remember that many of these granites intrude into fossil-bearing sedimentary rocks. One of those granites in southeastern Australia, you can actually walk from the fossil-bearing rocks, sedimentary rocks, through where the heat of the granite has metamorphosed the rocks and then into the granite. So we know that the granite formed after the sedimentary rocks formed with fossils in them. So when did the fossiliferous sedimentary rocks form? During the flood. That means 100 million years at least worth of radioactive decay in these granites had to occur during the flood. It's not that difficult to understand, is it? Now, in many granites, there are also single ring halos that are very small, sitting alongside the larger uranium radiohalos. And the larger one there's so much radioactivity that it's blurred all the rings. You can't see them all. So there's hundreds of millions of years worth of decay in that photograph. And in this one too. In some granites, in biotite flakes, we find 2 rings. The 2-ring one, that's very hard to see the outer ring, but it's there. It's there. And in some granites, you actually find 3-ringed halos. What does this mean? This is different to the 8-ring uranium radiohalos. Well, interestingly, these rings match the last 3 elements in that decay chain, well, the last 3 isotopes. It's all the same element. It's an element called polonium, discovered by Marie Curie and named after a homeland of Poland. It's a rare metal. And there's 3 isotopes in the decay chain of uranium, 218, 214, and 210. And so we find that these elements are responsible, this element, polonium, is responsible for forming these 1, 2, and 3-ring polonium, these radiohalos. And these polonium radiohalos are found in many granites around the world, alongside uranium radiohalos in Arizona, in South Australia, again in the Lake District of England. These are just a few examples. East of San Diego. But here's the problem. These polonium radiohalos have been described in a famous US court case as a very tiny mystery. It was the 1989 Arkansas trial. And on the witness stand was the Deputy Director of the US Geological Survey. And when he was confronted with this evidence, he scratched his head and said, it's just a mystery. Didn't have an answer. Why? Where did the polonium come from to produce these radiohalos? It's not in the biotite. The actual closest source is the uranium in the zircons, because remember, the uranium is decaying down to polonium as it's producing the uranium radiohalo. That means the polonium had to be scavenged from the zircon crystals as the uranium was decaying and transported to produce independent polonium radiohalos. That means the uranium and polonium radiohalos had to form at the same time. And here's the crux of the matter. The uranium must deliver enough polonium to generate 500 million to 1 billion alpha particles for each dark polonium radiohalide before the polonium decays. Okay, but what's the rate of decay of these polonium isotopes? Polonium-218 is 3.1 minutes. Polonium-214 is 164 microseconds. You blink and it's gone. And polonium-210 was 138 days. In other words, at least 100 million years worth of uranium decay had to occur while you blinked during the flood. So this is evidence, physical evidence, that not only that abundant nuclear decay has occurred during the flood, but there has been abundant nuclear decay. Millions, hundreds of millions of years of nuclear decay occurred within the single year of the flood. And you see what I mean? We've now got 4 independent lines of evidence that decay rates were accelerated during the flood. Well, there's